Bridge, the language model training stack. A language model is not one algorithm. It is a chain of decisions that turns raw text into a system that can predict and generate language. The first technical lecture moves quickly across that whole chain: tokenization, model architecture, optimization, hardware, scaling, data, evaluation, and inference. The goal of this bridge is to give every piece a stable place in your head before the lecture starts naming details. Think of the system as a pipeline with feedback. Data enters on one side. A trained model eventually comes out the other. Evaluation then tells us what to change, so the pipeline loops rather than ending. The pipeline begins with a question that sounds simple. What behavior do we want? A general language model is usually trained to predict the next token in text. That objective does not directly say, be helpful, write correct code, or reason carefully. It says, given the context so far, assign useful probabilities to what comes next. The model learns broad capabilities because predicting human text requires learning patterns about language, facts, style, code, and many kinds of reasoning. Later stages can shape the model toward specific behavior, but next token prediction is the central engine. Training examples are created by shifting a sequence by one position. If the sequence is the cat sat, the input might be the cat, while the targets are cat sat. In practice, the model predicts the target at every position in parallel. It sees the true earlier tokens rather than its own sampled guesses, an approach often called teacher forcing. This means one sequence supplies many prediction problems at once. The objective is simple enough to scale automatically across enormous text collections, which is a major reason it became so powerful. Before prediction can happen, raw text must become numbers. A tokenizer converts text into a sequence of token identifiers. Those identifiers are integers chosen from a fixed vocabulary. Common pieces of text may become one token, while rare words may become several. Byte pair encoding, or BPE, constructs this vocabulary by repeatedly merging frequent neighboring pieces. Tokenization is not just formatting. It determines sequence length, affects which languages and symbols are efficient, and changes how much computation the model must perform. The tokenizer is the entrance to the whole system. Compression is a useful way to judge tokenization. A common English word might compress several bytes into one token. A rare technical term, an unfamiliar language, or an unusual code fragment might require many tokens. More tokens mean a longer sequence, more attention work, more activation memory, and fewer words inside a fixed context window. A tokenizer trained on the wrong distribution can therefore make the model systematically more expensive for particular users. The vocabulary is part of the model's engineering budget, not a neutral dictionary. Token identifiers are still only labels. The model needs a useful numerical representation for each token, so it looks up an embedding vector. An embedding is a row of learned numbers. If the model width is 4,000, each token becomes a vector with 4,000 values. A batch of token sequences therefore becomes a three-dimensional tensor, whose major axes are batch, sequence position, and hidden dimension. You do not need to visualize every number. The useful mental model is a stack of spreadsheets, one sheet per example, one row per token position, and one column per learned feature. The transformer repeatedly updates those token representations. Attention moves information between positions. One token can gather relevant information from other tokens in the context. Feed-forward, or MLP layers, transform each position locally. Residual connections preserve an ongoing shared representation, and normalization keeps the numerical scale under control. Modern models vary the exact attention pattern, positional encoding, normalization rule, activation function, and MLP design. But the recurring question is stable. What information is routed? What is transformed? And how expensive is the operation? It helps to picture the residual stream as a shared workspace. Attention reads the workspace and writes back information gathered from other positions. The MLP reads the updated workspace and writes back a local transformation. Neither module has to replace everything already known. The residual connection lets each block contribute a correction. Repeating this pattern across many layers allows simple operations to compose into complex behavior. When the lecture compares transformer variants, the boxes may change, but the workspace, routing, transformation, and stabilization roles remain recognizable. At the top of the model, each token position produces a list of scores over the vocabulary. These raw scores are called logits. A softmax converts the logits into probabilities that add up to 1. During training, we know the correct next token from the dataset. The loss function compares the predicted probability distribution with that target. Cross-entropy loss becomes small when the correct token receives high probability and large when the model is confidently wrong. Perplexity is another way to summarize the same predictive uncertainty. Lower loss and lower perplexity generally mean the model predicts held-out text better.
The forward pass is everything required to produce those predictions and the loss. Training then runs the computation in reverse. Backpropagation uses the chain rule to determine how each parameter contributed to the final error. The result is a gradient for every trainable parameter. A gradient does not directly tell us the perfect parameter value. It tells us a local direction, a small change that should reduce the loss. An optimizer, such as Atom W, combines the current gradient with running statistics and chooses the actual update. That gives us the training loop. Select a batch of token sequences, run the forward pass, compute loss, run backward to compute gradients, apply the optimizer update, clear the old gradients, repeat. Around that simple loop are choices that determine whether training succeeds: learning rate, batch size, initialization, clipping, regularization, and the schedule that changes settings over time. At small scale, a poor choice wastes an afternoon. At frontier scale, the same kind of mistake can waste millions of dollars, so stability and predictability matter as much as peak quality. Training failure often appears as a numerical pattern before it appears as bad language. Activations may grow layer after layer. Gradient norms may spike. The loss may suddenly jump, become undefined, or stop improving. Initialization controls the scale at the beginning. Normalization and residual design control how signals propagate. Learning rate controls the size of each update, while clipping limits unusually large gradients. These mechanisms are different parts of one stability problem. Keep useful signal large enough to learn, but not so large that computation becomes chaotic.
The mathematical program has to run on physical hardware. Most model computation is matrix multiplication, and GPUs are designed to perform many matrix multiply operations in parallel. But arithmetic units cannot work until data reaches them. Model weights and activations live in high bandwidth memory, often called HBM, while computation happens in specialized cores. Moving bytes can take longer than multiplying them. This is why the lecture keeps returning to flops, memory bandwidth, arithmetic intensity, and hardware utilization. A fast algorithm is not merely one with fewer equations, it is one whose data movement and matrix shapes fit the machine. Resource accounting keeps 4 ledgers at once. Compute asks how many arithmetic operations are required. Memory capacity asks whether parameters, gradients, optimizer state, and activations fit. Bandwidth asks how many bytes must move each second. Communication asks what must cross links between devices. Improving one ledger can worsen another. Activation checkpointing reduces memory but repeats computation. Quantization reduces bytes but may complicate arithmetic. A larger batch can improve matrix efficiency but consume more activation memory. Systems work is the practice of balancing all 4 rather than optimizing one number in isolation. Framework operations are implemented by GPU kernels. A kernel is a program that runs on the accelerator. A single high-level line of PyTorch may launch one or several kernels. Launching many small kernels can waste time moving data and coordinating work. Fusion combines operations so data can be loaded once, transformed several times, and written back once. Tiling divides large operations into blocks that fit faster levels of memory. These ideas explain why 2 mathematically equivalent implementations can have very different wall clock performance.
One GPU is not enough for the largest models. Distributed training divides work and state across many accelerators. Data parallelism gives different examples to different workers. Tensor and pipeline parallelism divide model computation. Other strategies shard parameters, gradients, optimizer states, sequences, or experts. Every split introduces communication. Moving data between GPUs is slower than moving it within one GPU. So distributed training is an orchestration problem. Place the right data near the right computation and communicate only when necessary.
Imagine 8 GPUs that each process a different microbatch. Their local gradients describe different examples, but the model must receive one coherent update. An all-reduce operation combines those gradients and returns the result to every worker. That communication happens repeatedly during training. If computation finishes faster than gradients can move across the interconnect, adding more GPUs can make scaling inefficient. Distributed performance is therefore not simply single GPU speed multiplied by device count. It depends on how much useful work can happen between synchronization points. Once a training system works, scaling becomes a prediction problem. A scaling recipe maps a compute budget to a model configuration, dataset size, batch size, learning rate, and other settings. Researchers run smaller experiments, fit trends, and use them to predict larger runs. Compute optimal scaling asks how to divide a fixed budget between a larger model and more training tokens. The point is not that a simple law guarantees success. The point is to create a repeatable recipe whose behavior changes smoothly enough that small experiments tell us something trustworthy about expensive ones.
Suppose two proposed runs cost the same. One uses a larger model trained on fewer tokens. The other uses a smaller model trained on more tokens. The best choice depends on how loss changes with model size and data. Classic scaling studies estimate that relationship, but deployment can change the answer. A smaller model trained longer may be more expensive to create than necessary, yet much cheaper to serve millions of times. Training optimal and product optimal are not always identical. The scaling recipe must reflect the full life cycle, not only the pre-training bill. Data and evaluation close the loop. The model learns the distribution represented by its training data, so data selection is a form of product design. Crawling, filtering, deduplication, language balance, code quality, licensing, and contamination all affect the resulting model. Evaluation defines what success means. Internal metrics such as validation loss help compare training runs smoothly. External evaluations measure capabilities people care about, such as coding, multilingual understanding, instruction following, or long context reasoning. A model can improve on one measurement while becoming worse on another, so no single score is the whole story. Evaluation also has to be protected from the training process. If benchmark answers appear in the training data, a model may reproduce them without demonstrating the intended capability. This is contamination. A clean evaluation set should represent real use, remain separate from training, and expose trade-offs rather than hide them in one average. During development, smooth measurements are useful because they reveal whether a change helped consistently. At release time, realistic tasks matter because users experience behavior, not validation curves. Both views are necessary. After pre-training, additional stages shape how the model behaves for users. Instruction tuning teaches response formats and task behavior. Preference optimization or reinforcement learning can encourage helpfulness, safety, or other desired qualities. Inference is the separate systems problem of using the trained model efficiently. The prompt is processed in a parallel prefill phase, then output tokens are generated sequentially during decode. Caching, batching, quantization, speculative decoding, and specialized kernels all matter because the cost profile of inference differs from training. The complete map is now visible. Text becomes tokens, tokens become vectors. Transformer layers route and transform information. Logits become probabilities and loss. Backpropagation produces gradients. The optimizer updates parameters. Kernels and distributed systems make the loop fast enough to run. Scaling recipes decide what to train. Data and evaluation decide what the model becomes. Post-training and inference turn the trained predictor into a usable system. The first lecture will zoom in and out across this map. Whenever a new term appears, ask where it belongs, what information it consumes, what it produces, and which resource limits it. That question will keep the details connected.